My name is Alexei Demchenko, and I'm current chair of ACS Carb Division. We do have 2-year terms for chairs, and I'm probably going to be the first and hopefully the last chair who would never have a chance to actually attend the actual in-person meeting. Today it's my special privilege to introduce my graduate student, Catherine Alex. But before doing so, I would like to thank GlycoNet for welcoming ACS Carb. It's been a really wonderful collaboration. We learned a lot from you guys. Thank you for letting us use your platform. It's been a true pleasure, and we're looking forward to further collaboration and many more exciting presentations. So Catherine graduated from Indian Institute of Science, Education and Research in Pune, and she did masters there working with Professor Kikeri. It's the same institute where a few glycoscientists work, including Professor Hotta, who is known to many of us. She worked on glycodendrimers in Kikeri's lab, and soon thereafter she joined the PhD program at the University of Missouri in St. Louis, and also my lab. That was in 2016, so Catherine is nearing completion of her studies. She will definitely graduate in 2021, and today she's going to talk about her research dedicated to the synthesis of mannosides. And I was pleased to find out that there is actually a connection between Catherine's research and Jen Coller's research, because although Catherine will be mainly focusing on mannosylation, some of her microbial glycan targets have both L and D fucose residues. And without any further ado, Catherine, take it away.
So, hello everyone, I'm Catherine Alex, and I'm a 5th-year graduate student in Professor Demchenko's lab. And I'd like to thank everyone, especially GlycoNet and ACS Carb Division, for this wonderful opportunity. So today I'll be talking about the methodologies for stereocontrolled mannosylation with acidic and or aminosugars. So glycosylation is the cornerstone reaction in glycochemistry, where it links together a glycosyl donor and acceptor through this glycosidic bond. So with the activation of this promoter assisted leaving group, so the leaving group will be activated by the promoter, which is present at the anomeric center of the glycosyl donor. And upon activation, it forms this oxocarbenium ion, which can then be attacked by the incoming nucleophile, either from the top phase or from the bottom phase. So the top phase attack of the nucleophile results in 1,2-trans or the beta glycosides, and the bottom phase attack results in the formation of 1,2-cis or alpha glycosides. And apart from that, there are other side reactions that happen, and this itself complicates the process of achieving pure glycans. And hence, tremendous effort has been developed for the synthesis of glycans with excellent stereo control. So generally for 1,2-trans glycosides, we utilize the conventional neighboring group participation, where we use a acyl substituent that can form acyloxonium ion intermediate upon activation of the donor, and that will block the attack of the nucleophile from the cis phase, resulting in the formation of trans glycosides. And these methodologies have all been extensively discussed in this review that was published from our lab in 2015. And today I'll be talking more about H-bond mediated aglycone delivery method, which was developed in our lab in 2012. So in this method, the donor is equipped with a participating functionality at the remote positions of the sugar ring, which is C3, C4, and C6. And this is capable of forming this hydrogen bonding with the free hydroxyl unit of the incoming nucleophile. And that forms this hydrogen bond complex. And the stereoselectivity will be determined by the orientation of this complex, because the nucleophile will be delivered in a syn fashion with respect to the picoyl or picolinal group. So when you have a C4 picoyl group, in glucosides, this delivery happens from the bottom face of the ring, and that results in the formation of alpha glycosides. And as you can see from the examples here, excellent stereoselectivity and yield was obtained. And when this C4 is present in a galactose, it results in the delivery of nucleophile from the top face and resulting in the formation of beta glycosides. And when the picoyl group is present at the other remote positions, which is C3 or C6, the delivery of the nucleophile happens from the top face, and that results in the formation of beta glycosides. And this is really important in terms of mannosides, and that was published in 2014 from our lab. So we were able to obtain beta mannosides at ambient temperature using the HAD method. So the major advantage of this method is that it does not depend upon the orientation of the substituent at the C2 position, and hence it can be utilized for the synthesis of 1,2-cis as well as 1,2-trans glycosides. And also the introduction of the picoyl group and the removal is very easy, and that can be utilized for iterative glycosylation methods. And this is really important for the synthesis of mannosides, because in mannos series, they have the strong propensity to form 1,2-trans or the alpha glycosides because of the strong anomeric effect favored in this mannose series. And with the help of HAD method, we were able to synthesize this beta mannosides and in excellent yield. And there are other manno-configured sugars that are present abundantly in the bacterial glycans, like mannosamine, which has the C2 amino group. There is mannuronic acid, which has the C6 oxidized, and as well as the mannosamine uronic acid, which has the C2 amino group and the carboxyl at the C6 functionality. And these are like major constituents of microbial glycans, and mannosamine is also the synthetic precursor for N-acetylnuraminic acid. So these rare acidic amino sugars, they have not been explored well, and HAD method has never been applied for their synthesis, and that is what I'll be discussing further in this talk. So for the synthesis of mannosamine donor, we started with methyl glucoside and introduced the benzylidine at the C4 and C6 protection, and did the selective triflylation at C2 and epimerization to obtain the acido derivative of mannose. And then we did the acetylysis with N-sulfuric acid, followed by the acetyl glycosylation and deacetylation to obtain the triol derivative. And we further introduced the benzylidine group at C4 and C6. And then the C3 was protected with picolinic acid to obtain our mannosamine donor. And as a control, we introduced the benzoyl group to obtain the mannosamine control donor. So the difference here is in picoyl group, you have the nitrogen, which can act as the hydrogen bonding acceptor, and that is lacking in benzoyl group. So thereby we can study the differences of the glycosides formed. So we carried out several glycosylations with the standard acceptors. And with the C6 acceptor, we saw, and with the C3 picoyl group, we found that the desired disaccharides were formed in excellent stereoselectivity, with beta being the major one and good yields. And that trend continued for both C4 acceptors, C3 acceptors, as well as C2 acceptors. And the reason we have done here two methods are 5 and 50 millimolar concentration, because in the earlier studies we have seen the HAD method works better in the high dilution conditions, and it was also continuing the same trend. And when we utilized mannosyl donor with C3 benzoyl group, we found there is a switchable stereoselectivity, and there was formation of alpha disaccharides and in good yields, and the trend continued for both C6, C4, C3, and C2 acceptors. And the formation of these disaccharides were also confirmed with the coupling constant values. So for generally the beta disaccharides, they have the coupling constant of 160 Hertz, and for alpha it is 10 Hertz or more than the beta one. So the trend continued, and we were able to confirm that the HAD method indeed works for Mannosamine donors. And we extended this methodology for the synthesis of Streptococcus pneumoniae serotype 4 capsular polysaccharide repeating unit, which has this mannosamine connected to the fucosamine at the C3 position, as well as to galactose. And for the synthesis, we utilized our mannosyl donor and carried out the glycosylation with the C3 fucosamine acceptor to obtain our desired disaccharide in excellent yield and stereoselectivity. And the pickle oil group was then removed selectively using copper acetate to obtain the disaccharide acceptor. And then we carried out the second glycosylation with our galactosyl donor to obtain the desired trisaccharide repeating unit, and thereby showing that the methodology works for the synthesis of beta mannocytes. And for the synthesis of mannuronic acid donor, we started from the non-building block, which has 3 TBDMS and 4,6-benzylidene mannosyl derivative. We selectively opened the reductive opening of the benzylidene ring to 6-OH, was carried out using copper triflate and borane, and also removed the TBDMS group using TBAF to obtain the diol derivative. And then we carried out the oxidation of the primary hydroxyl. And in this reaction, we obtained a 3,6-lactone as well. And this was converted back to our desired acid using 1 molar lithium hydroxide. And once we had the acid in hand, we carried out this esterification with benzyl bromide to get the benzyl ester. And as for the synthesis of mannuronic acid donor, we introduced pickle oil group at C3 position. And as a control donor, we introduced benzoyl group at the C3 position to obtain the mannuronic acid control donors. And we carried out the glycosylations with the standard acceptors. So for 6-OH glycosyl acceptor, we saw that the yield and the disaccharide, the desired disaccharide was obtained in both 5 and 50 millimolar concentrations. And the trend continued with the 4-OH acceptor, 3-OH, as well as 2-OH acceptor, giving moderate to good yields of the desired beta disaccharides. And when we did the glycosylation with the C3 benzoyl group, the desired disaccharides were formed, and with excellent stereoselectivity, forming the alpha disaccharides. And all the disaccharide formation was confirmed with the coupling constant values as well. However, for the C3 acceptor, the 5 and 50 molar conditions they showed a drop in the stereoselectivity, and hence we wanted to further investigate, and we decided to do a glycosylation with mannuronic acid donor and mannuronic acid acceptor having the C3. And to our surprise, the reaction worked with an excellent stereoselectivity of giving 1 to 18, with the beta disaccharide being the major product. And then we continued with the pickle oil removal to obtain our disaccharide acceptor. And then we carried out the second glycosylation to get the trisaccharide, followed by pickle oil removal to obtain the trisaccharide acceptor. And then we carried out the last glycosylation with our mannuronic acid donor to obtain the desired tetrasaccharide with the 1,3 linkage, thereby showing that the methodology works indeed even for C3 acceptors. And for the mannosamine uronic acid donor synthesis, we started from the known mannosyl derivative and so did the selective reductive ring opening with copper triflate and borane to 6-OH. And then we carried out the oxidation of the hydroxyl group, the primary hydroxyl, to obtain the acid. And this reaction also yielded our 3,6-lactone, and that was converted back to our desired acid using lithium hydroxide. And once we had the acid, we did the esterification to get the benzyl ester. And then for ManNACA donor, we introduced the pickle oil group at C3 position, and as the control donor, we introduced the benzoyl group at the C3 position. And we carried out the glycosylations with the different donors and the standard acceptors. So for the 6OH acceptor, we obtained the disaccharide in having the excellent selectivity as well as the good yields. And the trend continued for C4 acceptors, C3 as well as C2 acceptors. And for the benzoyl containing ManNACA donor, we obtained the alpha disaccharides in excellent stereoselectivity and in good yields. And further, it was also confirmed with the coupling constant values. And then we decided to extend this methodology for synthesizing the trisaccharide repeating unit of the capsular polysaccharide of Staph aureus serotype 8. So this one has ManNACA residue, which is connected to L-fucosamine as well as D-fucosamine in 1,2-cis fashion. And for the synthesis, we started from ManNACA containing ManNACA donor and the L-fucosamine acceptor to get our desired disaccharide. And we obtained the disaccharide in excellent stereoselectivity and good yield of 61%. And once we had the disaccharide in hand, we removed the pickle oil group to obtain the disaccharide acceptor. And then we carried out the glycosylation with the D-fucosamine donor to obtain the capsular polysaccharide repeating unit in moderate yield and excellent stereoselectivity. So with this, I would like to conclude my talk by saying that by utilizing this HAD methodology, we were able to tackle these challenging beta monocytic linkages and was able to showcase this methodology for the synthesis of relevant oligosaccharides that are present in the microbial glycans. And these can indeed be used in developing carbohydrate-based vaccines. And now I'd like to now take this opportunity to thank Professor Demchenko for giving me this opportunity to work in his lab and for the continued support, and also for GlycoWorld past members and the current members and the University of Missouri, and also NIH NSF for the funding, and GlycoNet and ACS Carb division for this opportunity, for this wonderful opportunity for presenting in this webinar series. Thank you for your attention, and I'll take any questions.